I know a lot of you that know me and seen me up on the platform 100 times in my career, giving a talk now and then about this subject. Jeff Kalb and I were just musing about it at the hors d'oeuvre part of the meeting tonight that, the industry has changed so rapidly that you can always keep a set of slides, and if you keep them up to date, it's sort of, have slides, we'll travel, we'll talk. But I decided tonight I would try not to use slides, but I'll tell you, I feel very embarrassed trying to fill the shoes of Ed Teller. And I don't know, I'm pretty disappointed about the speaker's choice here. Well, I was just going to say, if you're half as disappointed as I am, we're going to be in for a tough 45 minutes. That's all I got to say. And I can tell you this, in all honesty, if it had been anyone other than Gwen Bell that called last week, I'd have said no way. But it's kind of hard to say no to Gwen Bell. After, and I think we all know her role and her position as, to me, it's both the creator and curator of this museum, and without her, I'm certain there wouldn't be a museum here, or at least it wouldn't be as great a museum as it is at the present time. Now, this entire story that Gwen is trying to document the history of the story, is really one of the most complex, most difficult achievements of man, I think, to try and properly document. It cuts across so many fields of human endeavor that I don't think anyone here tonight could sit down and list every field of endeavor that has contributed to it, and then every field of endeavor that it has affected. So from either aspect, we could both come up, I think we could all come up with some pretty long lists, but I think the lists would be pretty incomplete. And I think part of the problem is that the way we've been trained as engineers or scientists, every time we try to sit down and think about the history of, let's take the broad case of computation, although I'm going to talk about a narrow part of it, because we've been trained the way we do, we think everything ought to fit in a box. And so we either start with a decision tree, and we think that every great advance should be at the node of one of the decision tree, or we start with something that looks like a very convoluted organizational chart, and we think everything ought to go inside one of the boxes. And I think when you start that way to try and tell this very, very complex story, I think you run into a great deal of trouble. And I think it was described most beautifully in the little book Revolution in Miniature that was written by two professors from England, Stuart MacDonald and Ernest Braun, who said that this story, the story of computation, semiconductors and their contribution, what is it, can only be compared to a very beautifully woven piece of fabric. We see the finished fabric. We find it to be very pleasing, very beautiful, as a whole piece of cloth, but we pay little attention when we look at the cloth and find it to be a very beautiful piece. We pay very little attention to the individual fibers that form the warp and the woof of the cloth. And we are willing to admit that whatever beauty the cloth has must come from the individual fibers, but we miss the fibers and their part in the cloth. And I think this is the way it is with the story of computation today. The whole story is indeed a very beautiful, it turns out to be a very useful cloth, but the task of describing how each fiber in the finished cloth has contributed to both the utility and beauty of this finished tapestry is a nearly impossible task. And I find that if I take just one thread out of the cloth, and that's all I'm going to do tonight, is to pull out one thread from this cloth that's labeled The Story of the Silicon Chip. And I find that as I try and look at this one fiber from this whole cloth, the fiber itself seems to be rather complex and convoluted, and it's not one single strand. It has been spun from many strands. And you find that this individual strand is almost as complex and as convoluted as the original cloth was. And so I find that in the 45 minutes I will try to keep within, I cannot really describe the full complexity, the form and feature of this single fiber, and I doubt if I could do it if I took the time to write an entire book about it. But I don't think that one should take the time to recite the past without trying to learn something from the past and see how it might possibly affect the future. So I'm going to throw all caution to the wind at the end of the talk and see if I can perceive from the past some of the future trends. Now, I know I'm being videotaped, so I'll be rather cautious about these things, but if it turns out that at some future date somebody snickers about how short-sighted we've been here tonight, I'd just like to remind you that I'm in very good company. That some of you may know that in 1933, Fortune magazine ran a series of articles in which they interviewed all of the great physicists of the world who had contributed to physical theory as it was then known. And a lot of them were Europeans. At that time, Einstein had already come to the United States, and he was one that was interviewed. And we knew, of course, already at that time that as the nuclei of certain atoms were formed, much of the mass that was originally in the protons and neutrons that made up the nuclei disappeared. And so it was obvious that if man could find some process for either fusing the lighter elements into some of the heavier elements or splitting some of the very heavy elements into some of the lighter elements, those in the middle of the periodic table, that it would be one of the most enormous energy sources that man ever had come about. And if you will go back to the one issue, and I don't remember which issue, but it's in 1933, Fortune magazine, Einstein is quoted as saying that man will never split the atom. And we find that in general, no matter what our knowledge or our experience may be, that we almost always fall far short in trying to predict the future. Now then, I think there is one other caution I should point out here too, because the history that I will give of the story of the chip is a history according to the Gospel by Hogan. And I think that it's one of those things that we have all lived in a different environment. A lot of the research was done in industrial laboratories where it was held as proprietary information of many of the industrial laboratories. And it is very hard to unravel this thread that I'm going to try to unravel tonight, and to know exactly what did take place at what time. It reminds me of another story that Tyson had in the preface of his little book, Disturbing the Universe, and you may have read it. He recounts the story of a conversation some 50 years ago between Leo Szilard and Hans Bethe. And Leo Szilard told Hans Bethe, he said, you know, things are moving so rapidly that when this period of physics is over, we're never going to be able to recreate the history properly. And so he said, I have begun to take a diary. I have a diary that I write in every single night. And in fact, tonight, before I go to bed, the conversations you and I had, I'm going to record in this diary. And Hans Bethe said, do you hope to publish it at some time? And he said, oh no, I don't intend to ever publish it. And Hans Bethe said, why are you keeping it? He said, when it's over, I just want to make certain that God knows the truth. Well, it even gets better. And Hans turned to him a little surprised and said, Leo, don't you think God knows the truth? He said, of course he does, but I don't think he knows my version. So I want you to remember that it is my version, and there may be other versions that are available. I think to start with, I hope everyone in the audience knows that the chip began at Bell Telephone Laboratories really on December the 23rd, 1947. Now, certainly, there were hundreds of physicists before that time that had contributed their part to the understanding of the physics of solids before that event. I think one of the most remarkable things about this invention was the fact that Marvin Kelly, who was then president of Bell Labs, and Bill Shockley, who directed the physical research group, had publicly gone on record that they were looking for an amplifier. And that's how they justified the millions, and it wasn't hundreds of millions in those days, it was just a few millions of dollars a year that they were spending on research on these little tiny crystals of germanium. And for anyone who asked, they were told that they were trying to find a solid-state amplifier. And regardless, I think, of the other contributions, whatever they might have been, and I think no matter how close the brilliant researchers at Purdue University came to making the very same breakthrough that was made at Bell Telephone Laboratories, the breakthrough was made on the night of December the 23rd, just 2 days before Christmas in 1947. And the experiment that was being performed was to try and understand some peculiar data that had been arrived at before, whether they had brought two probes close together and found that under certain conditions, not all conditions, but under certain conditions, the one probe was able to modulate the spreading resistance in the germanium crystal. This is a total resistivity, if you like, that the probe sees in the probe that was sitting close by. Now that in itself doesn't imply amplification. It certainly implies that you can control the resistivity of a substance. But the conditions were just right on this evening, and they were working late in the evening that night, such that Bratton realized that he had amplification, that when he put small RF signals, and we shouldn't say RF, they were pretty low frequency, audio frequency signals, on one of the probes, he was able to get out an amplified copy of those signals from the other probe, between the probe and the crystal. And of course, the next day, everyone in the group at Bell Laboratories knew the results. And exactly what went on in the next few weeks, I think none of us are really going to know for certain until Bell Laboratories chooses to publish the engineering notebooks of all the individuals involved, and that may never be until all three of them die. But nevertheless, it appears that Shockley immediately made the intuitive leap from this point contact device to the PN-junction. And he went home and wrote the paper that was eventually published as the theory of PN junctions and PN junction transistors. And that still stands today as the great classical piece of work that established the whole story of the chip as we know it today. But Shockley was a very unusual person. He not only made the intuitive leap from these two little probes to the PN junction transistor, he also anticipated and patented the MOS transistor in the same period of time. He could not make the MOS transistor work. It did not work at Bell Laboratories. The reason it didn't work is because nobody understood the role of surface states at that time, and the minority carriers that he was trying to induce in his MOS transistor were trapped in the surface states, and the device never worked, and he never really quite understood at that time why it did not work. But the point contact transistor was a very unreliable transistor. I was talking to Ken, and he said the first ones he ever got at MIT came from France, and he thought they were a fraud. They didn't amplify. And I said, well, most of them didn't. I mean, they would for a while, but they didn't last very long. They were very unreliable devices. They were very difficult to manufacture. They could not be built. They were never built reproducibly. You could never find two with the same properties. And those properties changed so rapidly with time that even if you found two alike, the day after tomorrow, they weren't alike. And so by that time, of course, even when they had tried to build the point contact, Shockley had Shockley published the internal memo within Bell Laboratories within 2 weeks after the discovery. And you all know the paper. I presume you've all read the paper. So that whole piece of work was done in 2 weeks. So this, of course, the fact that the point contact device was such a cantankerous device justified enormous amounts of money to be put into the development of the PN junction transistor, which then everyone believed would have all the nice things that were in the first press release, infinite life, and a few other statements like that. And but nevertheless, there were a few problems left to be solved between that time and present time. And the first PN junction transistor was created in 1950 at Bell Labs. It was done by Gordon Teal with a grown junction technique where he grew a single crystal of germanium and dropped a pill in of molten germanium to change from N-type to P-type, and grew a little bit more, and then put in another pill to change it back to N-type, and grew a little bit more. And you hoped that you would get a planar junctions across there. They were not planar. They were very curved. The resistivity profile was terrible. The resistivity varied with radius as well as with length of the crystal. And even though the crystals were not much bigger around than my thumb at that time, they were not as exciting except for one particular thing. The first grown junction transistor proved quantitatively that Bill Shockley's theory was absolutely correct. One measured the resistivity of the emitter, the base and the collector regions, and measured the base widths. The theory was absolutely phenomenally accurate. And in that sense, it really is one of the greatest engineering papers of our time, because here's a man who closed the intuitive gap from that first point contact invented, if you like, the PN-junction transistor, worked out all of the theory in 2 weeks, published it internally within the laboratory, and it was 2.5 years later before Gordon Thiel got a PN-junction transistor working in order to check the theory, and the theory was quantitatively accurate. But nevertheless, it was a very low frequency device. It really only worked at audio frequencies, and whenever one tried to make that base region ever thinner, pretty soon it was too thin, and the emitter and collector were shorted together. And it just turned out that we realized very soon that this was not the way either to make transistors, that we had to find yet another way if we were going to ever achieve all of the remarks that had been made in the press release. But nevertheless, the transistors were indeed better than the point contact if you got them to work, and you got wires welded into the various regions and got it encapsulated. It at least worked, and it would work for many months before it ran into trouble. But the fact that the theory was accurate really got people interested, and it was, I think, in 1952, the Bell Labs had the first symposium at Bell Telephone Laboratories in which potential interested parties attended, and they offered a license to the industry, and many people took a license in that year, and the industry was off and running in 1952 with all kinds of people going in all kinds of directions trying to find another way. And there were many ways that came out, but as one looks back at that decade of the 1950s, it really is characterized almost entirely by what we would call today processing. There was no real, there was some design theory that was done, but it was rather unimportant. The important problem was, how are you going to make it? How are we going to control both the physical and the chemical geometry of these substances? We knew what we had to do. We had to grow extremely pure single crystals of either germanium or silicon at the time. Then we had to put impurities into that very, very pure crystal, such that we would have an N region, an electron region, a hole region, we call a P-type semiconductor, and then an N-type region, and have the regions close enough together, the base region thin enough, so that we could get high frequency performance and yet not have the emitter shorted to the collector. And so that's what the problem was that was attacked. There were many basic processes that developed. First, there was the problem of crystal growing. During World War II, we did a superb job of growing single crystals of materials that were soluble in water, even quartz, which was, if you like, was soluble in water. It's a hydrothermal process, very high pressure and very high temperature, and had a lot of lye in it in order to transport the quartz from hot to the cold part. But nevertheless, we grew some enormously large and good single crystals during World War II to solve a problem that we had in order to have these devices available for us for some of the technologies that we needed in the war. But we had not made much progress in growing single crystals of semiconductor type devices, which are metallic in appearance and have very high melting temperatures from 1,000 to 1,400 degrees centigrade. And especially when one realizes that you know, you have to have a crucible to hold them, and what kind of crucible are you going to have hold this thing at 1400 degrees centigrade and still have it come out with a purity level that had never been achieved by man before, except for a few very special materials like mercury. We had always been able to make mercury very pure and clean, but we had never achieved the kind of purities that we needed. And this in itself was a very, very difficult problem. Bill Fan came up at the time with the zone refining techniques. That is, if you have a material like germanium or silicon, and if you melt a region in the center and then move that molten zone through, the solubility of the impurities are different in the molten part than they are in the solid state. And it doesn't really hurt whether it's more or less. If it's more or less, then the impurities go to the left instead of to the right, you know. And so as you move the molten zone in through, if the impurities are more soluble in the molten state, then they tend to follow the molten state as it moves through the crystal. And if you make enough passes, you can just keep refining the crystal over and over and over again. And it turned out that we used that system because we didn't have any better way to do it at the time, back in the 1950s. But then we had to find other ways to make the transistor, and we came up with the alloy transistor, and then finally we learned how to diffuse impurities into it. That if we would take the crystals of germanium and silicon, put them in a furnace at a high temperature, not near the melting point, of course, and pass gases over the material, that the impurity would diffuse into the single crystal. And that could be controlled a lot better, a lot finer control than any of the others. And along with these basic metallurgical problems that we were trying to attack in the 1950s, there were many, many other problems, such as etching the junctions, washing, making very, very pure, and to start with distilled and then deionized water. How do you degrease the material without contaminating it? You know, how do you do the shaping of the crystal? You've got a crystal, you've got to saw it like slices of bologna, and you have to then polish it and etch the impurities off and get rid of the crystal damage that has been done by the slicing and polishing operations, and things like this. Now, it turns out that photoresist techniques for defining the mesa actually occurred before the planar transistor came along. And in fact, I find a lot of people don't know this, but it was published in what was then called the Proceedings of the IRE in 1957. Diamond Ordnance Fuse Laboratory were trying to make what we would today call a hybrid integrated circuit. They took little slabs of steatite ceramic, dug little wells in there, and glued down mesa transistors. Of course, they had silk-screened resistors on the ceramic, and they baked those in. And then they evaporated, believe it or not, aluminum from the contacts, the emitter and base contacts, on the mesa transistor down onto the steatite ceramic to connect these little transistors to the circuit itself, and to insulate the aluminum from the germanium so that the emitter contact would not short to the base and collector region. They actually painted it with photoresist and baked it on, and that became the insulating layer much as the silicon dioxide is the insulating layer today. And that work was done in 1956 and 1957. And again, this whole story of what preceded the final invention of the integrated circuit is itself a very long story. And I've bent Gwen's ear about this, and she has what I think is one of the most accurate stories of some of the basic contributions that were made in as the integrated circuit was developed. But nevertheless, in my opinion, the integrated circuit was invented by Bob Noyce, and I think Bob Noyce's integrated circuit is to the other integrated circuits that preceded it precisely what Bill Shockley's PN-junction transistor was to the point contact transistor. Now, it was necessary for these pioneering efforts to go on. Bill Shockley didn't invent the PN-junction transistor, it turns out, until Bardeen and Bratton told him about their point contact transistor. And so I guess that had to precede it. At least it's what got his mind working on the device we used. And it's possible that all of these other pioneering efforts in integrated circuits were required. But nevertheless, the integrated circuit then was invented by Bob Noyce. That about closes out the 1950 decade. I think the patent was applied for sometime in the summer of 1959. It says, again, Gwen has that particular patent on the wall. And I think we pretty well have covered that first decade. Basically, what we were trying to do in the 1950s is find a technique to make transistors that gave us more and better control over the properties itself, gave us reliability, gave us an ability to define the various regions in a much more exact way, and then associated all of the metallurgy that went into crystal growing and shaping and what have you. We were trying to get higher and higher frequencies as we did this because the first transistors we built were extremely low frequency. In fact, they were, as I pointed out, they were all audio frequency devices. It was a very exciting period, the 1950s, because new techniques kept tumbling out. It seems like, as you look back, almost on a weekly basis, there was something new. And one could not wait for any kind of an annual meeting to find out what was going on, because you'd be way behind time if you waited to learn about what was going on in the hallways of some annual meeting. So we had to keep in very close contact with each other, visit each other's laboratories almost on a monthly basis to keep up with the progress that was being made. I think there were a couple of lessons that we learned in the 1950s that may perhaps be valid today and might even be valid in the future. And I think the first thing we learned was that some of the big companies that were the richest, that had the greatest talent, and were indeed corporate giants, found they were in a business they didn't understand in the 1950s. And the laurels in that time went to those who were daring, who were flexible, and who, in every case, had technically oriented management. And again, I'll refer to an article that was in Fortune magazine, which I read very carefully, in 1953, in which they made it very evident that no one had a chance in the semiconductor field except these big giants, because the amount of research that was required in order to solve these myriad of problems were so great that no one had a chance, and they even listed the companies that would absolutely dominate the business some 10 years later. And on their list were RCA, General Electric, Sylvania, Raytheon. Certainly the people who were large in the vacuum tube business at the time. And if we go to 1958, just 5 years after the Fortune magazine article, and list the top 5 manufacturers in the United States, we started with Texas Instrument, which in 1950 was known as Geophysical Services Incorporated, was the corporate name of the company, in fact. And we find number 2 is a company up in your area, Transitron, was then the second largest manufacturer. And Philco, believe it or not, was the 3rd largest manufacturer of semiconductor devices in 1958. If one went down further down the list, you would find Hughes Aircraft down there on the list sometime. But then Transitron, who was number 2 in 1958, very rapidly began to fade. And Philco, who was number 3 in 1958, sold out to Ford Motor, you may recall, and Ford finally locked the door and threw the key away in 1968 and went out of the business. So even some of the newcomers to electronics, who rose rapidly and blazed like a beautiful skyrocket on the 4th of July, also sputtered just as rapidly and fell to the ground. Now, I think we could carry on a 2-hour, very lively discussion. Gee, I'm taking a lot of time. As to why they did, but I think in each case it's a different story. I don't think there is one story that accounts for everyone's failure. And there is a story that I think, if you want to understand a little bit more, that I think is a story worth telling, is the one about Philco. Because Philco invented the microalloy transistor and then developed it beyond that to the microalloy diffuse transistor. Now that was the best high-frequency transistor of its time. There was no transistor that came close to the MADT in the 1956-57 time frame as the Philco MADT. And they also built some of the most beautiful machines I have ever laid eyes on in our industry. These were machines that would cover that whole wall there. And they took a chip of germanium, a little tiny chip of germanium, about an 1/8 of an inch square, and untouched by human hands, this thing passed through this machine. It was jet etched from both sides to etch a little dimple into the germanium, and that etching continued until the amplitude of an infrared light passing through the crystal reached a certain magnitude, which turned off the jet etchers, and then there were plated into those little dimples the impurities that were then going to be alloyed in. They were then subsequently alloyed in, still with nobody touching anything. The whole machine kept control of this whole operation, and they were then alloyed in, and the little chips came off, and they were working transistors, hopefully. The problem was they moved dynamically. They had a good transistor. They had a lot of courage to build these machines at such an early date. I have no idea what they spent. They must have spent $50 million minimum on the design and construction of those machines. The only thing that happened that was a problem was that before the machines were debugged, the transistors were obsolete. It turned out there was no way of changing those machines to make either the germanium mesa or the silicon planar, which were made by entirely different techniques. And Philco just would not give up at the time. I think if Philco had recognized in 1958 that they'd been had, and that the only proper thing to do was not to go out and compete with the germanium mesa transistor, but to learn how to make it and at the same time make a very lucrative replacement market by selling the MADT at very high prices, they would have been a very profitable company for a very long time. I see Gordon wiping his forehead there. And turns out that, well, maybe for your sake and a few other computer manufacturers, lucky they didn't do that. But they should have done that for their own sake because it was destined to be the wrong thing to do and to try and use it to compete. And we faced this problem at Motorola in 1960 when we had the world by the tail in germanium mesa transistors, and Fairchild announced the silicon planar transistor. And so we made as profitable a business as you people would let us make on the germanium mesa transistor. And at the same time, we unleashed an enormous effort to try to learn how to make the silicon planar device. And it turns out we learned very well, because by 1964, we were selling as many silicon planar transistors as was Fairchild. And in 1968 is a year in which I happen to know both companies' sales quite accurately. Motorola sold in dollar volume twice the volume of Fairchild in silicon planar transistors alone. So it was a pretty interesting story. But I think the lessons that we had to learn was to be aggressive, be dynamic, be technologically daring, have technical management. It turns out that no one has won in this business without technical management. And but then have the willingness to give up your process and your technology just as rapidly as somebody shows you a better way to do it. I think it's a very important lesson for today, because I believe that we are reaching, I'm going to skip a lot of this because I'm taking up an awful lot of time. I think we are facing in the design of integrated circuits today, I think we are facing a very, very difficult problem. I think we're going to see more changes in the processing technology than we have seen for the last 20 years. You know, it turns out that if you just sit down and write down the steps of a planar process and don't worry about the details, they really haven't changed. Now, the details have changed, but number one, you take a silicon wafer, you stick it in a furnace, and you grow an oxide on it. You know, I see Jeff laughing. It's a little bit more complicated, Jeff. But then basically, this is the way it goes. And you take it out and you spin a photoresist on it, you see, so that then a photoresist that is sensitive to ultraviolet light, and somebody else in another part of the shop has made a mask for you, you know, and all you have to do is shine some ultraviolet light through the mask, and this exposes the photoresist. Then you develop the photoresist, and then you remove the photoresist, depending on whether it's positive or negative resist. You know, either one of them you remove it where the ultraviolet light is hit, and the other one you remove it where it hasn't hit, but that's a minor thing too. Then you leave that resist on, and so it protects the oxide, and then you etch the oxide away. And we used to do that wet chemistry. We're gradually changing that over to dry plasma, reactive ion etching, or what have you. Well, be that as it may, you just etch the oxide, and then you get rid of the resist and stick it back in the furnace again. And oil, you've got to put it in for diffusion or ion implantation. And there are a few minor changes there, whether it's diffusion or ion implantation. But then you put it back in the furnace, grow the oxide, and then they come to a statement that says, go to 1. And you go through the process again, you see. And that's roughly what the planar process is. And from there, we've made all these integrated circuits. But I have a feeling we're not going to push this technology much further. At least in the simple form that I've outlined it. we're having great trouble trying to push ultraviolet light into the 1 micron region. We've done it in R&D. Everyone's done it in R&D. But we're having enough trouble manufacturing 2 microns. And I just don't think we're going to push ultraviolet light down into micron level. If we do, I'll give you an idea. One thing I did do while I was thinking about this, I just took out a sheet of graph paper and I thought, let's see, how much did that first mask aligner cost and what kind of definition did we get? And so I just put a point on the graph. And then the first one that was available was Kulicke and Sofa, and then Casper, and then Cobalt, and then Perkin-Elmer, and now the direct step on wafer. And if you just draw that, the first one we ever built for ourselves cost us $1,000. And then when these fellows started building them for us, suddenly the price is $15,000. And then they got it up to $50,000 for mask aligner. And by that time, the management was having apoplexy. And everyone was trying to build a projection aligner because we were ripping up our photoresist. One of the problems with this is the mask was at that time an emulsion mask. And even though the silicon looks very smooth to your eye, you look at it under a very high-powered microscope, or certainly under a scanning electron microscope, it looks like the Swiss Alps. And we're ripping the emulsion off our masks. And, we had to replace the masks after about 50 alignments, and even then the yield was pretty bad if we used the mask for even 50 alignments. And so we wanted a projection aligner, and we all tried to make one, and everyone said, it's got to be easy. It's just like a slide projector, you just you stick the slide in here, and you put a lens in front of it, and you focus it onto the silicon wafer, The problem is we were talking about 1 micron dimensions, and we wanted a wafer that was 5 inches in diameter. And every time we'd go to a lens manufacturer, they'd look at us like we were crazy. And so it turns out that Perkin-Elmer finally solved the problem. A lot of people claimed to have solved it, and we bought a few of those, but they didn't work either. But Perkin-Elmer did solve the problem, and it was a magnificent invention. Truly a magnificent invention, and I think the fellow who did it did get a medal from the IEEE for it, and he deserves it, It was totally reflecting optics, no lens in the system at all, mumbo jumbo and magic right, you really can focus over a 5-inch wafer your mask with beautiful alignment, and we didn't run into any trouble at all till we got below 4 microns. And that took us to the 4 micron level, and now we're at direct step on wafer. We can only expose a part of the wafer at a time, and we have to move over and do another part, and and there are many alignments, and obviously this affects the throughput. But anyway, start talking about the graph I drew, and how much is the machine going to cost? Now, we started off at $1,000. I forgot to tell you, Perkin-Elmer came out at $250,000. And GCA came out about $500,000, and they now tell us they can really make it do the job it's supposed to do if we pay $800,000 for the machine. And remember, this is just mask alignment. This is just to expose the resist on the thing. And so I just drew my curve the other day, And Jeff, it's going to cost $1.7 million for one that'll take you to, I don't know how it's going to be done, but I know the cost. You see? It's going to cost $1.7 million to get you to 1 micron by that technique. So that I find to be very discouraging. And I think we have to find another way. And I don't know what that other way is going to be. What I would like to see, what I dream about at night, is some big machine like Philco had, you see? But it's all in a vacuum, you see? And I want to do everything inside one big vacuum. And I want to get all the impurities in there somehow. And I want to get the metal on, and I don't want to take it out of that vacuum until the silicon nitride coat is on, and then we can take it out, and hopefully it won't be so sensitive to the environment. But one can dream of these. You might say, well, that dream is so far away. You can conceive of how this might be done. If one goes to electron beam direct write and goes to dry plasma etching, and just take these coating machines and take them a level higher and include them in a part of the operation, one can imagine doing these things. There is a little startup company in your area in Beverly, Massachusetts, Ion Beam Technology, that is getting started, and I think there's some very bright young boys that are working on that. They have a long way to go, but their idea is to not use a mask at all, of any kind of mask, and to focus ion beams and shoot them in where you want them for the impurities, and just instead of drawing the thing with an electron beam on an electron resist, as what we've been doing up to now, is to just shoot the ions in where you need them, and we can anneal the damage out one way or another on that, but you know, that comes pretty close to my machine I've been dreaming about. And so I guess that's why I'm interested, and I hope they succeed. Because if they do succeed, then I think we have a chance of getting to the ultimate limits of silicon. It turns out that as I talk to my R&D people now, they have actually given up completely on the hope of ever getting below a 0.5 micron. And those are the courageous ones. The ones that are faint of heart have given up at 1 micron, and I just don't believe that. I think that eventually, whatever is possible, whatever the physical limitations of silicon are, we shall achieve. I think before I just drop that in the future, I'd like to tell you about what 2 other people that have good reputations in building computers anyway are trying to do. Seymour Cray doesn't want us to dice the wafer. He wants the wafer whole for memory. He doesn't want to ever go off chip. He wants all the memory together on a few wafers. He's going to coin stack these wafers, and he hopes then to get much higher speeds that way. And Gene Amdahl at Trilogy Systems is attempting to build himself. He's putting in a system to build all of the logic part of his computer on one single chip, which is 2 inches on a side. And he's spending a lot of money, I know that. And I asked him what the power dissipation was going to be, and one chip has to dissipate 1,500 watts. Now, you know, it's going to take a pretty good cooling system too, but he's not daunted by that problem. He thinks he knows how to do it. I told him when he comes to soldering the silicon down, I've had a lot of experience on the auto rectifier, and I could probably give him some hints, because that was one of the problems we had on the auto rectifier that we made for General Motors and Chrysler back in the early 60s, is we couldn't keep the silicon to stick to the copper at those terrible temperature extremes that one has under the hood of a car. And no matter what we soldered it with, it kept popping off. solder got cold worked and silicon would pop off. And it took us a while to solve that problem, but we did. And I told him for a reasonable fee I'll be his consultant if he happens to run into that problem, you know. And with 1.5 kilowatts being dissipated, he might just run into that problem, you know, trying to keep the silicon attached to the copper. But regardless of that, I think it's going to be a very exciting future. We really don't know how to define these geometries down to the ultimate limitation of silicon. We have great confidence that we can do 1 micron geometries, but that's a long way away from the ultimate limitations of silicon. I talked to Johnny Mayo at Bell Labs, and he scoffs at the faint of heart and tells me that in 10 years, our industry will put, if we don't, he will, put 1 billion components on a single chip of silicon. But however he does that, you know, it won't be with ultraviolet light and lenses and mirrors or anything else. There's got to be some other way to achieve that. I think it's going to be a very exciting 10 years, reminiscent of the 1950s, where there will be many proposals of how to break through this 1 micron barrier, and there will be many more proposals than we can all afford to try at one time. And we're going to have to be a little wiser than Philco was when they jumped on the MADT and built the world's best transistors, but you can't afford that if the machinery is obsolete before it's been debugged on the production line. And so I think by 1990, VLSI devices that are at least 1 inch square, and that's about half-fourth the area of Gene Omdahl's chip, with feature sizes at least as small as a 0.5 micron will exist. And that'll put a lot of devices on a single chip. I feel I'm not yet qualified to venture much beyond that, but I will leave that for another generation of engineers to come along and help to solve the myriad of problems that face us between now and that ultimate limit that we're all striving for. Thank you.